Yes, a good morning to you, my dear students. Yes, I want to welcome you to this lesson. As I start the lesson, allow me to announce that Teacher Kakuru D. Rwabinomi is my name. Teacher Kakuru has a YouTube channel that has various academic materials running from Senior Form 5, 6 on subject content, mathematics, physics. So far, you are encouraged to visit that channel on YouTube. Catch name is Ticha Kakuru D. Rwabinomi. The same teacher also has a digital study class on Let Us Learn from Home that is live right now, where I conduct lessons again for physics and maths, targeting Senior 4, Senior 3, Senior 5, and Senior 6. The same teacher has a slot on BBS TV during the COVID time and is teaching mathematics applied and physics too. Please catch up. I am sure as a student you will not regret. Today, we are going to look at a simple concept. I always tell my students that simple is relative, and its relativeness is in one's mind. But I will tell you it is simple, and as long as you believe it is simple, it will always be simple, as I normally say. Simple, straightforward. We are going to look at a concept that I believe we should be able to go through several examples, maybe 3 to 4 examples. I request that you have your calculators ready, because it will require you to use calculators. You have your pen, of course, and your paper or your book. We are going to look at linear, interpolation, and extrapolation. Extrapolation should have been one word. I have cut it off because of space. Linear, interpolation, and extrapolation. Linear, interpolation, and extrapolation. And we shall look at interpolation first. However, we need to note that both of them involve estimating a value of a function lying between two given values. Linear and extrapolations involve estimating. They both involve estimating a value of a function that lies between. It involves It involves estimating a value of a function that lies between two values, usually in the table or outside the table. I repeat that linear interpolation or extrapolation is a method that involves estimating a value of a function that lies between two values that are usually given in the table or outside the table. It requires us to, however, assume that the values of the function vary linearly. It requires one to assume that the values of the function vary linearly or in a linear proportion. And because we take that assumption that they vary linearly, we consider the use of gradients. And since we are saying they vary linearly, we know that for a straight line, the gradient between any 2 points of a line will always be equal. I will say, hence, we use the gradient between 2 points concept. We use the concept of gradient between 2 points we use the concept of the gradient between 2 points to be able to find the missing point. As I wind up with the introduction, I can say that for linear interpolation, estimation of the value between any 2 given points for linear interpolation, we do estimate the value of a quantity between 2 known values in a table. I want to emphasize that for linear interpolation, it requires estimation of a value of a quantity that is between 2 known values in a table. For extrapolation, we do estimate a value of a quantity falling between the known values of a quantity in the table. We estimate the value of a quantity that falls between the known values between the known values of a quantity in a table. Between the known values of a quantity in a table. And we are going to consider two cases. Consider case 1. If I have a table here, and this table has values of x and y, if this is x1, x2, x3, and their corresponding values of y are y1, y2, y3, then estimation of a value between, for example, x1 and x2 or x2 and x3 will involve what we have called linear interpolation. And estimation of a value before x1 or after x3 will involve what we call linear extrapolation. I want it to be very clear that estimation of a value that lies between, say, x1 and x2 or x2 and x3 requires linear interpolation. This is note number 1. Note number 2, estimation of a value that comes before x1 or after x3 requires linear extrapolation. Once those facts are well understood, then it becomes very easy for us to proceed. It implies that there is a value lying between x1 and x2 corresponding if we have a value lying between x1 and x2, and that value has a corresponding value on the y side, then we can be able to get whatever is missing between the two by referring to the already given pairs, as I will show you. If a value of x between x1 and x2 is say P, and its corresponding value on the y side is Q, then as I turn over, I can say that it would imply that my XY table for the part of interpolation, as we've said, this is x1, y1. But in between here, I've said there's a value PQ, and I have my x2, y2 over there. So if I called this A, B, C, I can use the gradient using, remember I've said there are points on a line, we assume a linear proportion, that the gradient between AB should be equal to the gradient between BC. Should be equal to the gradient between BC. Should be equal to the gradient between AC. As long as we compare this, it is also possible to compare this with that. As long as there is one letter being shared, we can compare. So if we consider AB gradient, if we consider gradient AB to be equal to gradient AC, the order will not matter. That our AB can be P minus change in Y. It is change in Y always for gradient, so we consider the Y differences. You should not forget that. So our gradient will be AB Q minus Y1 over change in Y over change in X over P minus X1 should be equal to AC. AC will be Y2 minus Y1 over X2 minus X1. This should be able to give us the value of one of the two if it is not known. Assuming all the others are known except one letter, we should be able to get its value. This is derived from the line. It comes from the line where we have point A, we have point B, and we have point C. Where point A is X1, Y1, point B is PQ, and point C is X2, Y2. So the gradient between A and B should be equal to the gradient between A and C. We use that simple approach. We can use other comparisons that I've said. One can use AB being equal to BC. Another one can use BC being equal to AC. These comparisons can also work. They can also work. So I can say note that other gradient comparisons can be used. You should not be rigid to only what has been shared in class, but we should know that other gradient comparisons can also work. And note number 2 is that the same approach or interpretation is used for extrapolation. The only difference here is that for extrapolation, our PQ kind of point is before or beyond the last set. And we can therefore say that the value of either P or Q can be obtained using the above comparison, provided or as long as all the rest of the values are known. All the rest are known except only one between P and Q. In other words, in mathematics we usually say if I have 1, 2, 3, 4, 5, 6, 7, 8 terms, if I have 7 of the 8, then the missing one can be found, as we shall see in our preceding examples. We can now look at the examples, and I request your calculator to be on standby. Very simple, very popular question, as we shall shortly be discovering from the question bank. The first example says, in the table below, is an extract of part of the logarithm of x to base 10. And the table is here. We have the value of x, we have its corresponding logarithm. 80.00, 80.20, 80.5, and 80.80. Corresponding value, if you are using your calculator to confirm, you can fix it to 5 significant figures or 4 decimal places, and just to confirm. Otherwise, if these figures are given to you, you are expected to follow the question using the figures given to you. So we are given this table for our first example. I want to welcome the students joining in. And usually when an example is done successfully well, it is always very simple for a student to try out the other numbers, as shall be the case after the lesson. We are required to use linear interpolation to estimate the value of the logarithm to the base 10 of 80.759, that is part A, and part B, to estimate the value of x that corresponds to the logarithm of 1.90388. And we shall go through the modalities of solving this right away. If you look at this figure, as a candidate, your task is to identify where does it fall. And like we saw in the example, we need to find a value that corresponds to that up there. So we shall let this log of 1080.759 be equal to a value I can call it P still, as I said in my example. So my table now is, my new table as I solve, is still in the same format. What do I need to identify? I need to identify only 3 values that we need to use. 3 values. And since we are using interpolation, the value we are looking for should be up, should be in the middle. So our 80.759 is here, and I've called this value P. That is for part A. 80.759 is between 80.50 and 80.80. So it means we have these values as I shared earlier, and we have only one missing value. So the concept we are using is the concept of gradient. By the way, it does not even matter if you chose to disobey the rules. Like gradient, we usually say change in y over change in x. But if it is not for the purposes of finding the equation of a line, you can consider either as long as you are consistent. So we can say that P, which is what we are looking for, minus P minus the value before 1.9058 over the change up there, P minus this, the ratio of this, over the ratio of the extreme, which is the big minus the small, 1.9074 minus 1.9058, as long as you maintain the pattern, should also be equal to the ratio of the corresponding differences. 80.759 minus 80.50 over 80.80, because it corresponds to this, minus 80.50. If we use this approach and do the mathematics, which I will expect you to do, you should be able to get the value of P as 1.907318. Try to confirm that when you simplify this, because you get this side multiplied by this difference and add on this, it will give you this answer. And this gives us the solution for part P. But the answers are recorded to 5 significant figures, so we must be able to conclude and let the final answer, which is the log of 10, 80.759, will be recorded as 1.9073 to 4 decimal places. That will be our answer for part A. As we proceed for part B, they want us to find the reverse, the log whose value is this. And we need to know where does it lie. 1.9038. 903, 903, 904. So this one must lie between these two. And therefore it means it is still an interpolation case. We can let the log of Q10 be equal to that value. So it means we shall be looking for the value which I have already called Q. So if I have my X and my log of 10 of X as the question is, we have identified where this one is lying, and there are 3 values we need only. So as we attempt to start our solution, we have 80.00, we have 1.9031, here we have 1.90388, this is Q now, and here we have 80.20, and the corresponding value is that. So we will use the same approach and say that Q minus 80.00 over 80 over 80.05. Here we are looking for this Q. So I have started with Q minus this. I can say divide by the corresponding difference of this should have been 5. Yeah, this is 800, and this, the value lies between these two. Yes, so my Q minus the 80 should be expressed over my 80.2. $80.2 minus 80, because yes, should be equivalent to my, now that I have worked with the numerators, I will start with this, should be equivalent to 1.90388 minus 1.9031 over, again, my 1.9042 minus 1.90388. $1.42 minus 1.9031. It is Q minus 80 over 80 minus 80 should be equal to this minus that over this minus that. Now, using your calculators, I want us to harmonize this. Using your calculators over here, I want us to harmonize this, and I will get the right hand side straight away. Our 1.90388, I request that you try it out for yourselves, minus 1.9031 should give us a value there. I'm doing it at a go, but I can say this is 7.8 times 10 to the negative 4. I am dividing this by 1.9042 minus 1.9031. This gives us 1.1 times 10 to the negative 3. And this is Q minus 80.00 over, I have 80.2, I'm taking away 80, and this gives us 0.2 here. So if we summarize this, so that it doesn't go beyond this page, by computing, we'll get our Q as 7.8 exponent negative 4 divided by 1.1 exponent negative 3, and then we multiply this by 0.2, and what we get, we add on 80. It should give us Q as 80.14. Since they are using two decimal places, this will be the answer, 80.14. 80.14 to 2 dps, 80.14. So basically, that would be the approach. Like I have shared, you could choose to use any other value other than the given value. Even if you chose the next value, because it's a linear interpolation, even if you skipped this and you used 80.50 and 1.9 or 80.8 and the other one, it would still arrive here at the same answer. It would still arrive here at the same answer. We can move on to another example. We can move on to another example, which I will call example 2. We can move on to another example, which I will call example 2. Example 2 says, study the table below. Study the table below. The table has x, and x is a function of f. We are given a table. For our second example, even if you joined late, you only need to be consistent, and you will be right over there by the end of the lesson. We have the table given as this 0.16, 0.48, 0.64, and they are saying using linear approximation, or otherwise it can be called interpolation or approximation. They are saying using that we should find part 1, f of 3 out of 2y. And then part 2, there are normally 2 parts on this question, and they take up the 5 marks. This is a section A question if it comes that brief. Then they also want us to find a value of n such that f of ny is 0.5. Such that f of ny is 0.5. As we have said in brief, that if the value they want lies or falls between, if the value they want falls between any of the 2 given values, in between, then we use interpolation. If it falls before or beyond the last, any of the last values, then we call it extrapolation. However, the working is the same, because linear or straight, and therefore we use the concept of gradient. We use the concept of gradient, only that here we are not rigid to the change in y over the change in x, as long as we are consistent. Now, our f of 3 over 2y is actually the same as f of 1.5y. This clearly shows you that it falls between y and 2y. It falls between y and 2y. So my x and f of x will allow me to now, me and you, to now capture the first value and then put our 1.5y here, and the value we want will be the value here. I will call it x. Since we have x already, let me call it a. I'll call it a. Let this be equal to a. And then we have 2y and 0.48. So by looking for the gradient, we can say, I told you the order does not matter. I can say y minus 1.5y over, I consider again y minus 2y. As long as I'm consistent, I used y and this, so I should use the same. Should be equal to 0.16 minus a over 0.16 minus 0.48. I am looking for a, this becomes minus 0.5y over minus y should be equal to 0.16 minus a over, when we subtract this we get negative 0.32. Now the negatives here will die, and the y will die as well. So we shall get our 0.16 minus a being equal to minus 5 out of 10 times 0.32, because the 0.32 goes there as a minus. So our a, if I took it the other side, will be equal to 0.16 plus, because a comes there and this comes there, 5 times 0.32 over 10. And our a mathematically will give us a value which should be equivalent to, our a mathematically will give us a value which we should compute to give us, ideally it should be greater than 0.16 but less than 0.48. So let us see. 0.5 negative negative y, negative y dies away, 0.5 is 5 times 0.32 divided by 10, which is 0.16. It will give us a value of 0.32. So our value of a will be 0.32, and therefore we can conclude and say that therefore our f of 3 out of 2y is 0.32. Like I said, any other option would be able to produce the same answer. If a student used, instead of this, they used 3y and 0.64, they would still get the same answer. For part 2, which I will put in this place, they want the value of n. So if this is n and f of ny is 0.5, it must be fitted between these three. So we have these from our table. We shall have this arrangement where this is x, this is f of x. For 2y I have 0.48, here I have 0.5, and here I have 0.64. And I want to show you that the order does not matter here. I can choose to use 0.5 minus 0.48 over 0.5 minus 0.64 should be equal to 0.5, which is ny, minus 2y over ny over 0.5 over ny minus 0.6. Okay, yeah, 0.64. If I choose to use that, I have 0.5 minus 0.48, which gives me 0.02 here. 0.5 minus 0.5 minus this should have been 0.64 minus 0.5. The order matters, that I'm starting with this minus that, and that means here I will have 3y. 0.5 is this minus this over 0.6 minus 0.5 should be equal to ny minus 2 over 3y minus ny. 3y minus ny. If I choose to use that, ny minus 2, then I have this minus that. So it means this over 0.64 minus 0.5, I get 0.14, will be equal to y into n minus 2 over y into 3 minus n. The y will cancel. I'm looking for n. This is the same as 2 out of 14. If I remove the decimal places by multiplying 100, will be equal to n minus 2 over 3 minus n. And therefore, this is 1, this is 7. I can say 3 minus n will be equal to 7n minus 14. My 8n will be equivalent to, my 8n will be equivalent to 17. Yes, 14 plus 3. And therefore, my n will be 17 out of 8, which, if we divide 17 by 8, will give me 2.125. And when we look at n, since they are looking for the value of n, we can conclude and therefore say that our value of n is 2.125. The order does not matter, but you must be consistent, as you saw me making adjustments here. Any other student that uses another approach but is consistent will always get the correct answer. We shall move to another example. And all these examples are unique and different. Keep taking note. I want to repeat that whoever is joining us right now should not get worried if they can only understand that interpolation requires us to get a value in between the given values. Example 3, they are saying the table shows values of x and f of x. Means x is a function of f of x, f of x, and the values are 2.11, 2.15, 2.19, and 2.23. These values have corresponding, the values of x have corresponding values of f of x. And the corresponding values of f of x 2.0143, 2.2345, 2.4979, and 2.8198. And they are saying we use linear extrapolation. We want to finish this. We have done the 2 examples on interpolation. Now, the next examples are for extrapolation. To find part 1, f of 2.09. In part 2, they want us to find f inverse of 3.0096. F inverse. Now, we have said that if it is extrapolation, the value they want us to find must be falling before or beyond the last given value. So in our solution, you clearly see that 2.09 comes before 2.11. So in our solution, our f of x must start with 2.09. And we don't know its value if we call it a. The next value is definitely 2.11 and 2.0143. And the order does not matter. The next value can be the very next value, can even be the last one. Why? We have argued that when you are looking for the gradient of a line, any 2 pairs along which the line passes will give us the gradient. So we are looking for a. and we shall use the gradient approach. The order does not matter. I will say the 2.15 minus 2.09 over my 2.11 minus 2.09 should be equal to, now we follow the order for the rest, to 2.2345 minus A over 2.0143 minus A. If I use this approach and simplify 2.15 minus 2.09, we obtain 0.06 here, over 2.11 minus 2.09, we obtain 0.02, will be equal to what we have here, 2.2345 minus A over 2.0143 minus A. But if we divide this, we get 3. So it means 3 into the denominator here, minus A, will be equal to 2.2345 minus A. And since our interest is A, it means that our 3A minus A, because this is going to be negative 3A, but when we take it to this side to become positive, and we take away that, and it should be equal to our 3 multiplied by 2.0143, which is 6.0429 minus 2.2345. So our A would be a half of this difference, minus 2.2345. A half of 3.8084, which will give us 1.9042. And if there are 4 decimal places, then it will be very clear that you can conclude and say f of 2.9 is 1.904 to 4 dps. You maintain the number of decimal places of the mother question as you conclude your answer. Alternatively, I have said the order does not matter. You could choose to use an alternative where you would get the things turned upside down. Instead of using the 2.15 minus 2.9, you could use 2.15 minus 2.11 over our 2.11 minus 2.09 would be equal to our 2.2345 minus our 2.0143 over our 2.0143 minus our A. If you compute, it should still be able to give you the A as the same. That's why I'm saying that you don't need to be rigid to my method of work as long as you have understood the concept. And that is what that's not what I normally refer to as understanding mathematics, not cram work. For part B or part 2, they want us to find the inverse, what we normally read as the inverse of this. But ideally, they are using that to actually check the student who may easily get be scared by numbers, that now the teacher did not talk about that inverse function. What do they want? You look at this, where does it lie between the given range? Remember, we said extrapolation, they give you a value that falls beyond. And since this is f of x, it means you have 2.19 because this falls beyond the last value of 2.819. So we shall use the last two values and 2.23, and we are looking for this, which I could call Q. They are telling you to find the value of Q. For 2.19, this is 2.4979. 2.23, this is 2.8198, and this is now 3.0096. So it is still the same question, the same working, by the way. We are looking for this value, and this number is so exact and so simple that you must be aware that your answer should be greater than 2.23. It's very simple and should be recorded to 2 decimal places. Why? Because they have already set the pace. So I have said if I call it Q, my Q minus the first value, for example, over my 2.23 minus the first value again. You must master that consistency, that one value is constant. And if you've started with Q, you start with the same function there. So 3.0096 minus the corresponding value of that, which is 2.4979, over 2.8198 minus again 2.4979. If you compute this and look for the value of Q, by now using your calculator, your Q value should be able to give you 2.2536, but remember that answers here are recorded to 3 significant figures. So you can conclude and say the inverse function of 3.0096 gives us 2.25 to 2 dps as our final answer. This is one of the easiest questions, I must say, and which is very, very common in exam. I repeat, which is very, very common in exam. I am going to do one last number for now. And then I will give you a trial exercise. One last number for now, and then I will give you a trial exercise. And as we meet to complete the remaining categories of examples, we will have a wind-up exercise. This is example number, I think, 4. Example number 4. All these examples are unique. I want to emphasize that the candidate must ensure that whether they are doing an interpolation or extrapolation number, they must make sure that their answers make sense. Your answers will make sense if their number of decimal places or significant figures tally with the initial number of DPs or significant figures given in the question. Example number 4, the table below shows an extract from tables of cosine of an angle x. The angle x is 80 degrees and its cosine is given with cumulative values, as we shall see. Now, when we are dealing with angles, we have what we call minutes. When I write this, it means I'm referring to minutes. These 10 minutes. We already looked at this. For those of you that have been consistent while we are looking at trigonometry and small angles, for those that have not been consistent and maybe attending this for the first time, you may not be in the know, but never mind, you are in the right hands. Now these values are given, of course, using a calculator and in mathematics to 4 decimal places. In physics practicals, we emphasize that we record 3 decimal places. And yes, here we are doing our last example for the day. On a topic that we have called interpolation and extrapolation. A very brief topic, but yet very popular in exam, as I'll keep emphasizing. They are saying we use linear interpolation. And I want to emphasize that when they say linear interpolation, it means that the values you are going to find should be between these given values. To find, 1, the cos of 80 degrees and 36 minutes, and 2, the cos inverse of 0.1685. I think you're beginning to get familiar. Solution number 1. 80 and 36 will fall between these two values, 30 and 40. So we shall get x as our 80 degrees, and we get the 30 minutes, the 36 minutes we are looking for, and the 40 minutes. We get their corresponding cosines. As provided for in the table. For 30 minutes, the cosine of x is 0.1650. For 40 minutes, the cosine is 0.1622. And this, I can call it x, okay, doesn't matter. But since we have this x, it is always advisable to use a different letter that does not clash with already given letters. Note one thing that I must emphasize here is that 1 degree is equal to 60 minutes. And this implies that this is read as 30 minutes. But 1 degree is equal to, and consequently I could say 1 minute is equal to 1 out of 60 degrees. The students should know that. Why this can help us if the values given were not in minutes in between here. But since they are all minutes, we shall simply say that 40 minus, and you indicate the minutes to distinguish it from just 40. 40 minus 30 minutes over 36 minutes minus 30 minutes should be equal to 0.1622 minus 0.1650 over y minus 0.1650. Again, like I said, if you compute this, you have 10 minutes over 6 minutes is equal to, the difference here will give you the negative 0.0028 if you compute, over y minus 0.1650. When we compute this, it gives us a value of y which we are looking for, equivalent 0.16332. But remember, we have 4 decimal places, and therefore our value for the cosine of 80 degrees 36 minutes would be 0.16334 dps. This is what I emphasized, that students must make sure that their answers make sense. The making of sense is indirectly interpreted that they should be in agreement with the given DPs at the start. As we wind up, we look at the last part of this question, which is part 2, where they want us to find the arc course of 0.1685. Remember, this is an extrapolation question. It's an interpolation question, sorry. The 0.1685 falls between 20 and 30. It falls between 1685. Falls between 10 and 20. So we have our x is equal to 80 degrees. We have our cos of x. And we are looking at 10. 10 is 0.1708. And in between here, we have what we are looking for, which gives us 0.1685. Then after that, we have our 20 minutes, and its corresponding cosine is 1679. So the arc course, we are looking for the arc cosine of that. And what is left is now history. It is now history. That I can say that my n minus 10 out of 20 minus 10 should be equal to 0.1685 minus 0.1708 out of 0.1679 minus 0.1708. The order does not matter, but you should always know what you are looking for. You should always know what you are looking for. This means that our n minus 10 over 10 should be equal to, when you subtract these, what do you get? 0.1685 minus 0.1708 will give me minus 2.3 times 10 to the negative 3 over 0.1679 minus 0.1708 give me minus 2.9 times 10 to the negative 3. This cancels, the negative cancels. My n minus 10 will be equal to what I have here, times 2.3 exponent negative 3 will give me the value of 2.3 divided by 2.9 multiplied by 10. This is 10 times 0.793. If I multiply this by 10, what I get, I'll add it on 10. What I get, I will add it on 10. And what do I have? I'll get a value that I will convert, of course, into, I'll get a value, my n will be equal to 10 minutes plus 7.93. So my n will approximately be 17.93 minutes, which you can round off to 18 minutes. And since we are looking for that, we can say that therefore the arc course of 0.1685 will actually be equal to 80 degrees 18 minutes. It will be 80 degrees. We must know how to conclude 18 minutes. If you forget the original 80 degrees, then here you will not be marked correct. You will not be marked correct. We will have some additional examples to look at when we meet next, but this is sufficient enough to allow me give you an exercise that will come your way shortly. I want to thank you for following. This is a combined lesson and I want to encourage you to start looking up for numbers of this nature in the question bank book. Whether you are in senior 5 or in senior 6, you are good to go here. The ones that fall under what we have not discussed yet, they will still use the same method, but they could have a different small technique. You could have a small technique, but which should not deter you from doing. For example, they may have an inverse function or a natural log function that may require you to know where to press, or the right press position or function to press on your calculator. I want to wish you the best of today and ask you to encourage your friends to subscribe to my YouTube account, Teacher T-I-C-H-A Kakuru D Wabinomi. Once you put in those 3, Teacher Kakuru D, it should be able to take you to the channel, to bring a channel where you should be able to see my picture, and the rest will be history. I'm uploading all the videos for these lessons and all the lessons that you probably could have missed, and all the cumulative lessons. There are so many. I'm still uploading them slowly by slowly. Like the page, but most importantly, use it to get the content. I wish you a good day. We catch up tomorrow. God bless you. Amen.